We can predict eclipses centuries in advance, yet we still can't fully predict what our own planet is going to do tomorrow. Today we're diving into 10 real-world mysteries. Massive Earth-scale systems behaving in ways that make scientists whisper, this shouldn't be possible. If you're interested in this topic, make sure to like the video and subscribe to the channel. It really motivates me to create more helpful content for you. So buckle up, because over the next few parts, we'll explore 10 massive anomalies, things scientists can measure but still can't explain. And if you think the world is predictable, stable, or completely understood, well, you're about to rethink everything. The magnetic pole sprint and Earth's invisible drift. You'd think that by now, we'd have Earth's magnetic field all figured out. It's just a giant bar magnet in the core, right? Simple, except it's not. The magnetic North Pole is on the move, and it's not just strolling, it's basically sprinting. For most of the 20th century, it wandered slowly around northern Canada, drifting a few kilometers per year. But since the late 1990s, scientists have watched it accelerate dramatically, racing towards Siberia at speeds of 40 to 50 kilometers per year. That's fast enough that global navigation systems, which used to be updated every 5 years, suddenly needed emergency corrections just to keep compasses and GPS-aligned maps from going out of date. This invisible drift is tracked by the World Magnetic Model, the reference used by everything from smartphone compasses and aircraft autopilots to military navigation systems. Normally it behaves like a polite guest, slow, predictable, no surprises. But in recent years, the field has started acting more like a glitchy GPS. The North Magnetic Pole isn't just moving faster, it's moving in a way that doesn't perfectly match older models of how the molten iron in Earth's outer core should be flowing. Scientists like Dr. William Brown at the British Geological Survey and teams working with ESA's swarm satellites have been mapping these changes in detail. They've found something even stranger while the overall field is drifting. Certain regions are weakening, like over the South Atlantic, while others, like over Siberia, are strengthening. It's as if someone is quietly tugging and twisting the planet's magnetic blanket from below. Here's where it gets really interesting. The movement of the poles and the shifting strength of the field seem to be connected to magnetic jerks, sudden changes in the magnetic field that show up every few years in observatory records. They're not literally too regular to be natural, but they are surprisingly sharp, like the planet's core occasionally twitching. These jerks appear to be linked to waves of molten metal racing through the outer core thousands of kilometers below our feet. Imagine gigantic metal tides sloshing around, changing how the field lines thread through space. And this isn't just an abstract physics problem. Animals that rely on magnetism, like migratory birds, sea turtles, and even some bacteria, use the magnetic field as a kind of built-in GPS. When the field shifts quickly, it's like nature quietly remaps the highways without updating the drivers. There's growing evidence that unusual strandings and route changes in some species may be tied to regions where the magnetic field is changing fastest. For a bird flying thousands of kilometers, even a small shift in the magnetic map can add hundreds of kilometers of error. Does this mean we're heading into a full-blown magnetic reversal right now? North becoming south and vice versa? Not necessarily. Full reversals in the geological record take thousands of years, and what we're seeing could be part of a smaller wobble or reorganization. But the speed and complexity of the current changes are forcing geophysicists to admit something humbling. Our simple dipole model of Earth's magnetism is more like a rough sketch than a finished blueprint. And if you think an invisible shifting magnetic shield is weird, wait until you hear about rivers of water vapor flowing across the sky where no water source should exist. The atmospheric river invasion. You'd assume that if you want a river, you need at least one basic ingredient: water. Oceans help, lakes help, moist air helps. What doesn't help is the Sahara Desert. And yet that's exactly where something impossible has been happening. Atmospheric rivers. Those airborne conveyor belts of concentrated water vapor, stretching for thousands of kilometers, usually form when moist ocean air meets strong winds. They're responsible for a huge portion of the planet's rainfall, especially along coastlines. But in 2023, something bizarre showed up on NOAA and ESA satellite imagery: long, coherent, moisture-packed atmospheric rivers forming over landlocked deserts with no nearby source of water. Dr. Marty Ralph, one of the world's top atmospheric river experts from UC San Diego, studied one such event over the Sahara and found it was transporting the equivalent of 20 Mississippi rivers worth of water vapor. That alone is wild, but the real head-scratcher is how the moisture survives. Normally, dry desert air acts like a sponge, tearing apart any passing humidity. But these atmospheric rivers weren't evaporating. They weren't even weakening. They were strengthening as they traveled deeper inland, as if being mysteriously refilled. The measurements get stranger. Radio sondes launched into these landlocked rivers returned humidity values that exceeded what the surrounding temperatures should physically allow according to basic thermodynamics. It's a bit like seeing someone carry 20 grocery bags in each hand when their arms should realistically only hold 2. The math shouldn't work, but there it is. Some meteorologists suspect that extreme warming of certain desert surfaces might briefly supercharge evaporation, but the numbers still don't add up. Others think that large-scale atmospheric waves, giant ripples in the jet stream, could be trapping moisture and pushing it along like a conveyor belt. NASA's recent satellite data even hints that electromagnetic effects from solar activity may subtly influence how water vapor clusters and moves, something we're only beginning to study. Nothing supernatural here, but definitely weird physics territory. And here's the part that really gets the scientific community buzzing. These desert atmospheric rivers sometimes produce sudden intense rainstorms that drop several inches of rain in mere hours in places where annual rainfall is almost zero. That kind of precipitation usually requires an ocean-fed storm system. It's like seeing a tropical downpour in a place where tropical anything shouldn't exist. Even weirder, some of the rainfall collected from these events contains isotopic signatures, basically the chemical fingerprints of water that don't match local or oceanic sources. It's still normal H2O, of course, but the ratios of oxygen and hydrogen isotopes suggest the water vapor had a very unusual journey, one we don't have a complete explanation for yet. As atmospheric science digs deeper, one thing is becoming clear. The rules we thought governed where moisture can travel and how long it can survive might be far more flexible than textbooks imply. And if the skies above deserts can suddenly behave like oceans, then it's not surprising that the oceans themselves have started behaving, well, rebelliously. Because next we're heading straight into the Gulf Stream, the powerhouse ocean current that seems to have developed a mind of its own. The Ocean Current Rebellion. You'd think the oceans, the biggest, heaviest moving things on the planet, would at least be predictable. After all, the Gulf Stream has been flowing along the east coast of North America for thousands of years, like a massive, dependable highway of warm water. But starting around 2019, scientists noticed something unsettling. Parts of this ancient current were suddenly turning around. Imagine driving down a 4-lane freeway and noticing one lane flowing backward. Not slowing down, not stopping, actually reversing direction. That's what researchers like Dr. Stefan Rahmstorff from the Potsdam Institute observed in sections of the Gulf Stream. Long stretches of the current were flowing south instead of north for months at a time. Something that shouldn't be physically possible given the stable pressures, temperatures, and Earth's rotation that normally lock these currents into place. But the ocean wasn't done breaking the rules. Even when the flow reversed, the water temperature didn't. Warm tropical water still found ways to move north, maintaining temperatures that should have required northward flow. In ocean physics, temperature and flow direction are basically married, and the Gulf Stream was acting like it had filed for divorce. Satellites like Sentinel-6 and Jason-3 captured massive spinning ocean eddies, some the size of entire states, forming and dissolving unpredictably. And here's the kicker, many of these eddies were rotating the wrong way for the northern hemisphere. As if Coriolis forces, one of the most foundational rules of rotating planets, had simply been ignored for a moment. Then came the biological surprises. Fishermen off the coast of Massachusetts started reporting tropical fish species in waters far too cold for them just a decade ago. Marine biologists were puzzled. How did these species survive the trip? Did they ride some kind of hidden express lane of warm water? Are we seeing a temporary disruption or a permanent rearrangement of the North Atlantic circulatory system? Meanwhile, Argo floats those robotic probes drifting thousands of meters underwater. Detected that these current reversals extend all the way down to depths of 3,000 meters. For reference, that's deeper than most of the Titanic wreck site. Traditionally, oceanographers assumed the deep ocean was insulated from rapid changes happening at the surface. The new data suggests everything from top to bottom is shifting together. A growing body of research is exploring a surprising connection. Electromagnetic disturbances in the magnetosphere seem to correlate with some Gulf Stream reversals. Not in a conspiratorial way, but in an our instruments are picking up something real and we don't understand it yet way. The idea is that small changes in Earth's magnetic field may subtly affect how conductive seawater flows. Water is full of charged ions after all, and charged fluids can behave strangely under shifting magnetic forces. But here's the most poetic twist. Plankton communities seem to notice changes before our instruments do. Marine biologists observed that some plankton species begin reorganizing themselves hours before current reversal signatures appear in ocean sensors, as if they're picking up environmental cues we still can't detect. If the oceans, the planet's thermal engine, are behaving in new ways, it raises a deeper question. What else beneath our feet is changing? Because next we're heading into the frozen north, where the Arctic permafrost has started doing something that sounds completely contradictory, melting and expanding it at the same time. The Permafrost Paradox. You'd expect frozen ground to behave like well-frozen ground. Either it melts because things warm up, or it stays frozen because things stay cold. But in the Arctic, the climate seems to have skipped the script entirely. Scientists monitoring permafrost, those thick layers of frozen soil that have locked up ancient carbon for millennia, are reporting something that sounds like a contradiction. In some regions, the permafrost is melting faster than models ever predicted, releasing methane and causing the ground to collapse into sinkholes. Yet in nearby regions, only a few kilometers away, permafrost is actually expanding, cooling, or even refreezing deeper layers at the very same time. Dr. Vladimir Romanovsky from the University of Alaska Fairbanks has documented these strange temperature inversions. In one borehole, the top layers warmed rapidly, while the deeper layers cooled a pattern that breaks the known rules of heat transfer. Heat is supposed to move downward or disperse outward. Instead, the Arctic permafrost is acting like it has invisible pockets of heating and cooling switching on and off independently. Ground-penetrating radar adds to the mystery. Boundaries between frozen and thawed soil appear to migrate horizontally and vertically by tens of meters in a single day. That's not just fast, it's thermodynamically bizarre. Soil doesn't heat or cool with the flick of a switch, but something seems to be applying energy in a way that looks targeted. Arctic scientists are also seeing wild swings in greenhouse gas behavior. Some sections of permafrost are releasing methane at more than 100 times typical levels, enough to cause local atmospheric spikes visible on satellite sensors. Yet just a short distance away, other sections appear to be absorbing gases, almost like carbon sinks. That's like having one patch of ground belching out carbon while the next patch acts like a forest in overdrive. Even carbon dating has entered the twilight zone. In some permafrost cores, surface layers test thousands of years older than the layers beneath them. It's not that time has reversed. It's more likely that rapid mixing, strange freeze-thaw cycling, or unknown chemical processes are scrambling the normal age signals. Still, it's the kind of finding that makes geologists rub their temples. NASA's MODIS and Landsat satellites reveal another layer of confusion. Surface temperatures recorded from space often disagree with ground sensors by 10 to 25 degrees. This isn't a machine error issue. These instruments are very precise. It suggests that something about the permafrost's physical structure is messing with how infrared sensors interpret the surface. Perhaps unusual water-ice mixtures, perhaps lensing effects from crystalline structures, perhaps something else entirely. And if that's not enough, seismic sensors are picking up micro-earthquakes as permafrost shifts. These quakes don't line up with thawing alone. Some resemble the patterns of rock cracking under structural stress. It hints that the ground isn't just warming or cooling, it's rearranging itself. Electromagnetic surveys add the final twist. The electrical conductivity of frozen ground is fluctuating in ways unrelated to temperature or water content. That implies strange phase transitions, changes in the structure of ice and soil that don't match known physics. Put simply, the Arctic is acting like a system undergoing rapid, uneven, and poorly understood transformation. The permafrost isn't just thawing, it's behaving like a living, reactive layer. And if the solid ground beneath us can surprise scientists this dramatically, wait until you see what's happening far above us in the electrically charged frontier between Earth and space. The Ionospheric Chaos. You'd expect the ionosphere, that thin, electrically charged shell high above Earth, to behave like a calm, predictable buffer between us and space. After all, it's mostly shaped by the sun. When solar activity goes up, it gets more energized. When the sun quiets down, it settles. Simple cause, simple effect. Except lately, it hasn't been simple at all. Dr. Jeffrey Forbes from the University of Colorado and multiple satellite missions have recorded bursts of electrical activity in the ionosphere that are far too strong to be explained by solar energy alone. Some regions are generating charges hundreds to thousands of times higher than incoming radiation should allow. It's like plugging your phone into a wall outlet and discovering it's somehow drawing power from a second invisible electrical source. Signals from communication satellites confirm the weirdness. GPS beams passing through these charged layers bend, twist, and scatter in ways that don't match forecasts. Typically, when GPS glitches happen, space weather experts check for solar storms, but lately instruments show clean solar conditions while the ionosphere behaves like a nightclub with the lights flickering and the speakers crackling. Radar networks, including high-frequency systems like HARP and ISCAT, have watched plasma structures emerge in geometric shapes. Not random blobs, organized stable forms, triangles, hexagons, rectangles. Atmospheric plasma should behave like smoke in the wind, chaotic, constantly dispersing. Instead, these shapes persist for hours, defying the turbulence of the upper atmosphere. You could forgive the scientists staring at these images for wondering whether nature is doing some kind of cosmic geometry homework. Temperatures in the ionosphere should roughly track solar input too. But recent measurements show layers heating to several thousand Kelvin even during quiet solar periods. Again, it's as if an unknown heater is switching on from the inside out. Perhaps the most astonishing discovery is that the ionosphere is altering Earth's global electrical circuit, the giant planet-wide system that controls how charge moves between the ground clouds and upper atmosphere. Typically, the potential difference between the ground and the ionosphere sits around 250,000 volts. Lately, it's been spiking to 400,000, 500,000, and occasionally beyond. Lightning patterns on Earth are shifting in response. Clear sky lightning bolts striking from empty blue air are showing up in places that historically never saw them. And these aren't small flickers, they carry billions of joules, the kind of power usually reserved for towering thunderheads. One surprising finding detailed in recent Nature geoscience papers is a possible connection between deep geological activity and upper atmosphere disturbances. Some earthquakes seem to trigger ionospheric anomalies hours before they even occur, hinting that electrical or acoustic waves may travel upward from Earth's crust long before seismic waves reach the surface. It's the kind of Earth-space interaction scientists once considered fringe. Now it's in peer-reviewed journals. Then there are the pulses. Defense meteorological satellites have detected electromagnetic bursts descending from the ionosphere toward Earth, pulsing in defined frequencies and repeating sequences. Not alien signals, let's be very clear, but certainly not random crackles of natural static either. They resemble patterned emissions we don't fully understand. And this brings us to a profound realization. Earth's upper atmosphere isn't just reacting to the sun. It's interacting with the crust, the oceans, the magnetic field forming a complex feedback-rich web scientists are only starting to map. But if gravity is supposed to be the least mysterious force, why are we suddenly seeing places where gravity itself begins to wobble? Because next we're entering the gravity anomaly zones regions where physics behaves like it momentarily forgets the rules. The gravity anomaly zones. Gravity is supposed to be the grown-up of the physical forces, steady, responsible, predictably tugging downward at 9.8 meters per second squared. It doesn't glitch. It doesn't improvise. It doesn't wake up one morning and decide to be different. Yet that's exactly what scientists are seeing in certain places around the world. Gravity fluctuating in ways that simply should not happen. Dr. Carla Briggenberg and teams using ultra-sensitive Lacoste-Romberg gravimeters have recorded daily variations in gravitational acceleration far beyond the margin of error, sometimes changing by 50 to 200 microgoults in under 24 hours. To put that in perspective, that's the kind of change you'd expect if billions of tons of rock suddenly shifted underground. But no seismic activity, no eruptions, no soundings, nothing. Even stranger gravimeters spread thousands of kilometers apart sometimes pick up the same fluctuations at the same time, as if gravity in different parts of the world is somehow coordinating its mood swings. According to Newton and Einstein, this should be impossible. Gravity responds to local mass. It doesn't sync up like a global playlist. Data from the GRACE follow-on satellites, which map Earth's gravity field from orbit, only deepens the mystery. They're seeing temporary gravity bubbles, areas where gravity weakens or strengthens for days or weeks before vanishing again without any corresponding changes in groundwater tectonics or ice volume, the usual suspects behind short-term gravitational shifts. It's like watching dents appear and disappear in a trampoline with no one jumping on it. Local effects are equally bizarre. In some regions, weather patterns seem to warp around gravity anomaly zones. Air pressure systems bend strangely. Wind directions shift unpredictably, and temperature inversions appear without the normal atmospheric triggers. It's as if the atmosphere is feeling something we can't see. Then there's the time issue. Precision atomic clocks placed in gravity anomaly zones have shown time dilation effects that exceed predictions by up to 40%. According to relativity, stronger gravity should slow time, but these clocks slow down far more than gravity measurements should allow. Either the clocks are wrong unlikely, or something is modifying local space-time curvature in ways existing physics can't account for. Ocean tides add another plot twist. In coastal regions with gravity anomalies, tidal heights don't match what lunar and solar gravitational pull should produce. The water is rising higher or lower than predicted, which means something is adding or subtracting to Earth's gravitational tug. Underground gravimetric surveys reveal phantom structures, dense or hollow regions that appear in one measurement and vanish in the next. It's not literal mass teleportation, it's that the gravitational signature is changing without geological processes behind it. That invites two possibilities. Either our instruments are sensing a new type of mass behavior, or gravity itself is fluctuating independently of mass. And here's the detail that keeps physicists awake at night. Some of these fluctuations follow mathematical patterns that look eerily like signals, periodic oscillations, modulated amplitudes, structured frequencies. Not random noise, not geological chatter, something organized. But let's step back. No one thinks gravity is breaking. More likely, we're glimpsing layers of Earth's systems that interact in ways we've never measured before. Gravity may not be as passive as we assumed. It might respond to deep Earth processes, magnetic reorganizations, or even redistribution of energy below our resolution. And if gravity, the quiet, stable anchor of physics, is shifting before our eyes, what does that say about the electrical storms happening right above our heads? Because next, we're heading into one of the strangest phenomena of all, lightning, that forms without cloud storms, that appear from blue skies, and electrical surges that behave like the atmosphere suddenly forgot how to be air. The atmospheric electrical storm. Lightning has rules. At least that's what we thought. You need clouds. You need moisture. You need updrafts tossing ice particles around like a cosmic blender, separating electrical charges until they snap back together in a giant spark. That's Lightning 101, the stuff every meteorology student learns on day one. But lately, Earth has been rewriting its own textbook. Dr. Earl Williams at MIT's Lincoln Laboratory has documented powerful lightning strikes emerging from clear blue skies. No clouds, no humidity, no storm systems within hundreds of miles. These clear-air lightning events carry billions of joules of energy, the kind normally reserved for towering cumulonimbus giants, yet they erupt in conditions where charge separation should be impossible. Electric field mills and loop antennas placed around the world are catching spikes of atmospheric energy that don't correlate with rainfall, humidity, or convection. Instead, lightning frequency is increasing by 15 to 25% per year. In some drying regions, the exact opposite of what classical atmospheric electricity predicts. You'd expect fewer storms when there's less water. Instead, the atmosphere is acting like it's becoming more electrically active on its own. Radio frequency monitoring adds another twist. Lightning discharges in these anomalous storms emit clean structured signals in the 8 to 30 kHz range, crisp frequencies with repeating patterns. Natural lightning usually looks like chaotic noise. These look organized. Not artificial, not technological, but structured in a way that hints at some underlying atmospheric rhythm we don't yet understand. Global lightning maps, like those maintained by the Worldwide Lightning Location Network, reveal synchronized bursts across continents. Bolts firing simultaneously in regions separated by thousands of miles, with no storm fronts linking them. That shouldn't happen. Lightning is a local phenomenon. But lately, parts of Earth's atmosphere seem to be listening to each other. Ground currents after these storms are equally baffling. Instead of dissipating within seconds, as all models expect, some regions measure electrical flows of 10 to 100 amperes lingering for hours. That means the atmosphere isn't just discharging electricity, it's storing it, redirecting it, or channeling it through pathways we've never mapped. Atmospheric chemists are also raising eyebrows. Air samples gathered during these electrical events contain molecular byproducts that imply energy levels 5 to 10 times greater than the lightning bolts themselves deliver. More ozone, more nitrogen compounds, more ionized particles. It's like something in the atmosphere is amplifying the chemical effects of lightning beyond what the raw electrical output can explain. And then there's ball lightning, those rare floating spheres of plasma that usually blink out in seconds. During these clear-air electrical storms, researchers and pilots have reported them lasting minutes. They drift. They hold shape. They move as if guided by magnetic or electrical gradients invisible to us. Plasma physicists are fascinated and admittedly a little stumped because these behaviors require extremely stable energy conditions. Finally, global atmospheric measurements show that Earth's entire electrical circuit, the massive planet-wide battery formed between the ground and the ionosphere, is running hotter than ever. Voltages are 50 to 100% above their historical baselines. Something is charging the planet more efficiently than thunderstorms and solar radiation account for. Which brings us to one of the strangest environmental twists of all in some places. Earth's magnetic field isn't just drifting, it's flipping back and forth like a broken compass. Because next we move into regions where magnetic polarity can reverse within hours, something once thought physically impossible. The magnetic field flip-flop. Magnetic reversals are supposed to take thousands of years. That's what geology textbooks promise. Earth's core churns slowly, the field weakens. Poles drift and eventually north becomes south, and south becomes north. A long, stately planetary waltz. But in certain regions today, Earth seems to have abandoned the waltz entirely and gone full breakdance. Dr. Monika Korter at the GFZ German Research Center for Geosciences has documented regional magnetic reversals happening not over millennia, but within 24 to 48 hours. Entire patches of land spanning hundreds of square kilometers suddenly show reversed polarity, as if the magnetic field in that area decided to flip reboot and try something new. Precision magnetometers reveal compass readings swinging wildly by 90, 120, even 180 degrees between morning and evening. It's like nature is playing tricks on navigation instruments. These reversals don't line up with solar storms. They don't show correlations with known geological features. They don't even match local conductivity changes in the crust, which physicists would normally expect to drive magnetic anomalies. What's even stranger is the impact on wildlife. Many species, especially migratory ones, carry their own magnetic GPS. Birds fitted with satellite tags suddenly veer hundreds of kilometers off route. Sea turtles appear confused during beach navigation. Even tiny organisms like magnetotactic bacteria, microscopic swimmers that align to magnetic fields, behave as if their internal compass needles are spinning. It's as if the magnetic map printed into millions of years of evolution is suddenly glitching in real time. Satellite data from ESA's Swarm constellation has revealed layers of complexity behind these flip-flops. The reversals appear in multiple regions around the globe at nearly the same moment. This timing hints at a coordinated driver, not isolated geological quirks. Something is disturbing localized pockets of the magnetic field at a scale too large for anything near the surface to cause. Underground electrical current measurements add another layer to the puzzle. Magnetotelluric surveys detect strong, unusual electrical flows during these reversals currents that don't follow the rules of induction described by Faraday's law. Ordinarily, magnetic fields induce currents. But in some cases, researchers suspect the opposite may be happening: electrical currents forcing magnetic field changes. If true, that would rewrite large portions of classical electromagnetism. Geomagnetic observatories have also noticed that these local reversals ripple upward into the magnetosphere, Earth's magnetic bubble in space, disrupting satellite electronics and affecting long-range radio signals. It suggests the phenomenon doesn't stop at the ground. It climbs upward into the sky, influencing systems thousands of kilometers away. Some paleomagnetic researchers are revisiting ancient anomalies in rock layers, wondering if rapid reversals may have happened before and the geological record simply smoothed them out over time. Magnetic minerals freeze in place slowly. Maybe we've always been blind to short-lived magnetic flips. If the world's magnetic field, our invisible planetary shield, can reverse itself on a whim in some regions, then what about the systems that depend on it? Could this connect to the bizarre swings we see in atmospheric chemistry, or the odd fluctuations in the carbon cycle? Because next we're diving into a mystery that touches every breath we take: carbon dioxide rising and falling in ways no model can explain. The carbon cycle breakdown. Carbon dioxide is supposed to be one of the most well-understood molecules in climate science. We know where it comes from: fossil fuels, respiration, volcanoes, and we know where it goes: forests, ocean, soil. The carbon cycle is the backbone of climate models, the cash flow system of Earth's atmosphere. But over the past decade, scientists have been watching the numbers do something deeply unsettling. They're no longer adding up. Dr. Peter Tanz from NOAA's Earth System Research Laboratory, one of the world's leading atmospheric carbon experts, has reported CO2 fluctuations so rapid, rising or falling by 15 to 40 parts per million in just weeks, that they break every known rule of carbon cycling. For comparison, the normal seasonal swing takes a full year to move by that amount. These new fluctuations happen faster than forests can grow, faster than oceans can absorb, faster than microbes can breathe. Something is pushing and pulling carbon around the planet like an invisible hand with impossible speed. Regional measurements paint an even stranger picture. CO2 towers in places like Alaska, Japan, and Europe have recorded neighboring sites where carbon levels differ dramatically, even when the land use, vegetation, and weather patterns are nearly identical. It's as if the atmosphere has started developing hotspots and cold spots of carbon dioxide that don't align with human activity or natural patterns. Then there's the isotopic mystery. Carbon molecules come with chemical fingerprints. Fossil fuels have one fingerprint. Plant respiration has another. Volcanoes have another. Yet some of the new atmospheric carbon spikes carry isotopic ratios that don't match any known source. It's still CO2, nothing alien here. But the ratio of carbon-13 to carbon-12 suggests processes that either don't exist on Earth or have never been detected until now. Oceans, which usually act as stabilizers, aren't following the script either. Autonomous buoys in the Pacific and Atlantic have recorded oceanic CO2 levels increasing, while atmospheric CO2 in the same region decreases, a direct violation of Henry's law, which says gases should move toward equilibrium. It's like the ocean and air have stopped talking to each other. Soils, meanwhile, are acting strangely. Automated underground chambers show carbon content swinging by 20 to 50% in just months, which would require microbes to work at impossible speeds or soil to exhale and inhale carbon like a lung on fast forward. Some regions are releasing far more CO2 than expected, while others appear to be absorbing huge quantities without any clear biological reason. Plants are joining the rebellion too. Eddy covariance towers, those weird-looking forest instruments that measure gas flows, have observed plants absorbing carbon at night when photosynthesis shouldn't be happening at all, and releasing carbon during the day at rates far above their metabolic limits. It's not that trees suddenly learned a new trick. It's that something is skewing the measurements in ways scientists can't yet decode. Climate modelers have tried plugging these anomalies into simulations, and the models break. Mass doesn't balance. Carbon appears and disappears. The ledger of the planet's carbon budget refuses to reconcile. A few emerging theories hint at possibilities previously unknown: chemical reactions in the upper atmosphere, rapid exchanges between deep ocean layers and the surface, even the influence of shifting magnetic fields on ionized carbon molecules. None are confirmed, but all show how interconnected Earth systems might be. And that brings us to our final mystery, one that ties all of these threads together. Because deep underground, the planet itself is rumbling in ways that don't fit what we know about tectonics timing, or even the physics of how rock breaks. Next, we step into the seismic pattern revolution, where earthquakes are happening, where they shouldn't, skipping their usual rhythms and behaving as if something beneath the surface has changed. The seismic pattern revolution. Earthquakes are supposed to follow rules. Not perfectly, nature always throws curveballs, but the broad strokes are clear. Fault lines build tension, pressure accumulates over decades or centuries, and eventually the rock snaps. Boom! Earthquake. Aftershocks follow predictable decay patterns. Quiet periods happen where expected. And stable continental interiors stay, well, stable. But lately, Earth has been acting like it misplaced the rulebook. Dr. Seth Stein of Northwestern University has documented major quakes magnitude 6 and above, striking regions considered geologically dead. Places like Central Australia, Eastern Canada, and the American Midwest, where the crust hasn't been tectonically active for tens of millions of years. The amount of stress needed to fracture rock in these regions shouldn't exist, yet the planet is cracking anyway. Even stranger is the timing. Global seismic networks have observed earthquakes on opposite sides of the world occurring within hours of each other without being connected by known stress transfer mechanisms. Normally, stress doesn't travel fast enough through the crust to synchronize quakes across continents. But something else might be transmitting energy or signals much more quickly. Then there are the deep quakes, shocks occurring 600 kilometers below the surface in zones where rock is so hot and plastic it shouldn't be able to break at all. But seismologists see clear P waves and S waves, the seismic signatures of brittle failure. It's like trying to snap a piece of warm clay and hearing it crack like glass. Seismic tomography, essentially CAT scans of the Earth, is revealing another twist. After some major earthquakes, the internal structure of the crust appears to change rapidly. Layers that should be stable over millions of years shift their seismic signatures within weeks. That's not enough time for geological processes to rearrange solid rock. It suggests the planet is undergoing rapid dynamic changes we don't yet understand. And then come the aftershocks. According to Anomaly's law, aftershocks fade in a smooth, predictable curve. But recent sequences look chaotic. Some regions experience aftershock swarms months after quakes when they should be calm. Others stop suddenly, then restart without warning. It's like the crust is trembling for reasons unrelated to the original quake. What's even more startling, total global seismic energy is rising. More energy is being released by earthquakes than tectonic plate motions alone can explain. Either strain is accumulating faster, impossible at known plate speeds, or additional forces are adding energy into the system. Here's where things get truly mind-expanding. Some researchers have found correlations between seismic anomalies and disturbances in Earth's magnetic field and ionosphere. In some cases, ionospheric weirdness appears hours before an earthquake, like the upper atmosphere senses something brewing deep underground. This isn't yet mainstream consensus, but peer-reviewed papers are piling up, suggesting electromagnetic precursors to seismic events. Could shifting magnetic fields influence stress in certain minerals? Could electrical currents in the crust play a role? These ideas sound fringe, until the data keeps showing up. What we're witnessing is a planet whose internal rhythms are speeding up, reorganizing, or behaving in new ways. And when we step back to look at all these mysteries together, shifting magnetic poles, rebellious ocean currents, desert, atmospheric rivers, gravity fluctuations, electrical storms, carbon cycle anomalies, and now unpredictable earthquakes. A pattern begins to emerge. Earth isn't breaking, it's changing, and possibly revealing connections between systems we never realized were linked. Now let's bring this entire journey home. Think back to some of the most astonishing moments. Magnetic poles racing across the planet like they're late for a cosmic appointment. Atmospheric rivers appearing over deserts with no ocean in sight. The Gulf Stream reversing direction, defying centuries of fluid dynamics. Gravity flickering ever so slightly as if space-time itself were breathing. And earthquakes erupting in places where the crust should be sleeping. And how many other surprises are waiting in the data just beyond our current understanding? Now it's your turn. Thanks for watching until the end. If you enjoyed today's video, please like and subscribe. It really helps me out a lot. Which of these mysteries blew your mind the most? The pole sprint, the desert rivers, the clear sky lightning, the gravity glitches. If you love learning how weird and wonderful our planet really is, make sure to subscribe for more science mysteries every week. Because the more we explore the stranger and more spectacular Earth becomes.